Alright class, we are back at it again, starting a brand new unit looking at energy. Now, you might have looked at a little bit of energy in middle school, so this might be kind of review material for you. Some it may be new, some it may won't, but I'm going to kind of start from scratch. This is lesson 1. Okay, where's my clicker? There we go. So, what is the law of conservation of energy? That's kind of the first statement we're going to make, is that energy cannot be created or destroyed. That's it. If you were to simply put the law of conservation of energy, the super simple definition could be energy cannot be created or destroyed. It can only be changed from one form to another. So I'm kind of like, think about energy as like my bank account. So I got some money in my bank account. When I spend that money, it goes into somebody else's bank account. Could be Walmart, could be I could have bought something off of Facebook, could be something else, but that money doesn't disappear. It only goes from one place to another. Same thing with energy. It only goes from one place to another. Some words that you're allowed to use when you're talking about energy. You can talk about energy being generated, transformed, or converted. But you can't talk about, which is not really helpful, you can't create or make energy. You can't even whip it up. Okay? It only is generated or transformed, or the word I like to use most, converted from one form into another. Well, then what is energy? What is this money? Well, energy is defined as the ability to do work. Work is kind of something we will unpack later and truly what that means. So energy is either doing something or able to do something. In the same way, my money is either being spent or has the ability to be spent. So when we think about the big whole, I would say everything, if I were to draw this circle here, and say the whole universe is in it. The universe is made up of primarily two things: energy and matter. Now, what we're going to learn next semester is the law of conservation of mass, is that matter cannot be created or destroyed. We're going to kind of put that off on the sidebar right now and say we'll only look at energy. So we're only looking at, let's say, half of what the universe holds. And the ability to do work is going to be considered energy. Now, there is something a little bit interesting about the relationship between mass and energy, that they do hold a little bit of an interesting relationship. And the only reason I'm bringing this up is because some of us know about Einstein's equation of E equals mc squared. You've probably seen it drawn on something or written up somewhere or on a mug. But there actually is a connection between mass and energy, and it's a huge energy release. So if we were to take one paper clip and convert it into pure energy, and that relationship it holds, you could power New York City for an entire year. I mean, the amount of energy in mass in itself is massive. We're not going to really unpack it beyond that, but there is a relationship there using Einstein's equation of E equals mc squared, but we're not going to unpack it beyond that. We will talk about a couple of types of energy as far as this class goes. Well, the type of energy we're going to talk about is called mechanical energy. So all energy is divided into kind of two basic banks. One is potential energy and the other is kinetic energy. You might have heard these terms in middle school. Kinetic energy is the energy of motion. We'll kind of unpack that later. And potential energy, there's a couple of different ways potential energy can kind of be observed. We're going to look at this first one, looking at gravitational potential energy, of looking at the energy of an object being stored based on its position. But I get there when I get there. The one thing we probably won't talk about in this class is chemical potential energy, because that deals with more chemistry. We're going to kind of look at just gravitational potential energy and elastic potential energy. Okay, so all of energy is divided kind of into two basic banks. We'll just circle them here. Potential energy and kinetic energy. And then in the potential energy, we'll look at two of them specifically. We'll look at gravitational and elastic. Okay. I digress. Let's move on. Let's look at potential energy. Well, what is it? Potential energy is energy of position or storage. So you kind of look at, let's look at this first picture right here. We have a dam and it's holding back a lot of water. That water is considered a high energy state because if the dam were to be removed all of a sudden, all of that water in that position would rush and cause a change in work to be done. Same thing when you look at batteries. Batteries have an electrical charge running through them, and it's stored in its container ready to be used. So it's a energy of position, talking about the water dam, or energy in storage, looking at a battery. What if we were to have a bow and arrow? So if we look at this bow and arrow, this picture right here on this kid, there is a lot of energy stored in the position that this bow is making. And that is where that elastic potential energy comes from. So the position of this bow tells me that there's going to be stored energy in the flex of the bow. What's the last one I like to talk about, at least anyways, is if we were to look at something really, really high up in the air. If we were to take a soccer ball and kick it really high in the air, since that position, so let's draw a little picture over here. Let's draw me standing down here, and I were to kick a soccer ball really high in the air. This soccer ball has a position to where it is able to do some work. It is going to come back down eventually. So, looking at a couple different types of energy, let's look at how do we calculate or how do we look at potential energy of a position. What we won't do is we're not really going to look at potential energy in food. That's kind of chemistry related stuff. We're really not even going to look at potential energy right now of a bow and arrow because that deals with hooks and springs, or Hooke's law and springs. And we're also not really going to even look at potential energy of a battery because that deals with a little bit more complicated physics and also some more chemistry as well. What we are going to look at is energy of position, and we call that gravitational potential energy, which is this formula right here. So if we were to look at a bungee jumper jumping off of a really, really tall platform, he has an amount of stored potential energy at the top of the cliff before he jumps off. Well, where does that energy come from? Well, that energy comes from three variables. First one being mass, which we already know mass. That's still going to be in kilograms, so we'll do kgs for that. Acceleration due to gravity, that 9.8 number is coming back again, meters per second squared. And then the height of an object, which is going to be in meters. Let's just do over here, let's do m for meters. So if my object is either heavier or in a taller place, we can then say that the potential energy is going to increase. Okay, let's apply this and let's find the potential energy of a couple different systems. Okay, before I forget though, what is the measurement or the unit we use for gravitational potential energy? And that is joules. So the kind of way we looked at all forces being in newtons, anything in energy in this class will be in joules, and we'll use the letter J. Okay. All right, let's try this problem out. I want you to just pause on the video, try it out, read the question, maybe write down what you have so far, and try the problem on your own. Okay. All right. I'm going to draw a picture. As with all problems in this class, drawing a picture is going to be helpful. So here's my cart. is at the top of a 300-meter hill. This is a 300-meter hill. And has a mass of 40 kilograms. What is the cart's gravitational potential energy? Well, since this is energy looking at position, this is stored energy. So we're going to use P equals mgh. For looking for potential energy, mass of the cart is 40 kilograms. Gravity is still 9.8. And then the height of the object is 300 meters. So let's try that. So let's look at that. It's going to be 40 times 9.8 times 300. And that gets me a very large number. And that's okay, because energy, a joule, isn't a particularly big number. So sometimes when you measure stuff out in joules and how much energy it is going to be a very large number. There we go. We found the potential energy of the object. Let's try this one out.
Oh!
I'm going to tweak this, and I'm going to say this apple has a mass of, let's say, 0.05 kilograms. Okay. We were going to have to convert, but you don't have to convert on your homework, so I'm not going to do it here. We're looking for the height of the apple. Okay, so go ahead and pause the video, try it on your own, and then see if you get the same answer as me. We're looking for height here. Okay. Like we do with anything, we're going to draw a picture. Let's draw a red apple. There we go. Let's give it a green leaf. And let's give it a, I can't really do a brown stem, but let's do a black stem. Okay. And this apple has some amount of energy. Let's say 175 joules. I have a feeling I made a really, really tall tree. We'll see in a second. It has 175 joules of energy, and it has a mass of 0.05 kilograms. And the potential energy of it is 175 joules. Let's try this out. So P equals mgh. Potential energy is 175. Mass is 0.05. Gravity is 9.8. And we do not know the height of our object. Okay. Some people have a hard time looking at the algebra here, so let's take it step by step. I can clean this up just a little bit by looking at these first two numbers, 0.05 times 9.8. So let's do that. 0.05 times 9.8. And that gets me 0.49. Ooh, I made a really tall tree. H, 0.49 H. Let's divide both sides by 0.49. And we get the height of the tree. It's going to be a big tree. Divided by 0.49. 357. Woohoo! That's taller than a football field. 357 point, let's do 14 meters. Okay. That's it. We're looking at potential energy. What is going on here? Well, this is the energy of storage. So the higher the object is, the more energy it's going to have, or the heavier the object is, the more gravitational potential energy it might have. Here in a second, we're going to connect the two types of energies we're going to talk about, potential and kinetic, but we're going to kind of put a pause on potential energy for right now. Okay? Let's look at kinetic energy. Kinetic energy is the energy of motion. So if something's not in a position, but instead of it's moving, like Forrest Gump running, for example. All right, Forrest Gump running is energy of motion. That means Forrest Gump has some sort of kinetic energy. If we were to look at any objects moving, like this, I don't know what this groovy train is doing in the outer space, but if an object is traveling in outer space, like a satellite or a rocket or this mystical train, it's going to have some sort of speed, which means it has a kinetic energy. What happens if we go a little bit bigger? Like, let's think about planetary objects. Well, planetary objects also have a kinetic energy. So we think about the planets revolving around the sun. And as they travel around the sun, they're moving, and they also have a kinetic energy as well. If we think about the atoms, like the smallest particle that we can observe without retaining its characteristics, if we look at the smallest particles of matter that we're going to go as far as in this class, say for now, as the atom. Atoms also have kinetic energy. We just called the heat. So if you think about when you put something in the microwave, what happens here is that the atoms get really, really excited. And as they get excited, they heat up. Well, when those molecules are bouncing off each other, all going all kinds of crazy fast, that is actually what causes a release of heat. They're bouncing in a bunch of different directions. So when atoms are going really, really fast, that's when stuff is hot. One thing we might talk about eventually is, well, what happens when atoms get so cold they stop moving? And that's a really, really cold temperature, but I'm going to save that for next semester. Okay, so not only do we look at really, really small stuff having kinetic energy, we can look at really, really large stuff. So, but in general, what we're going to say is that kinetic energy is the energy of motion. Okay, how do we calculate? How do we find kinetic energy? Well, kinetic energy is using this formula. Mass is still in kilograms, so what we're going to do is say kinetic energy used, so it's energy, so energy is going to be in joules. Mass is in kilograms, and velocity is meters per second. Ooh, we have velocity coming back. Okay. The only thing that some people do get tripped up on is that there is a squared relationship in this equation. So the velocity squared. Okay, we're going to practice this here in a moment. But I want us to point out the fact that this is 1/2 times m times v squared. So the only thing we're actually going to be squaring is the velocity. That these two numbers, I guess 1/2 mass and velocity, you don't square anything else other than velocity. I've got a couple of students who kind of one thing they love to do is they'll just type this all on their calculator, 1/2, and they'll put times mass times velocity squared, and if they accidentally don't pay attention, it'll square the whole thing. And that's something we do not want. We do not want. This is bad. Right? Don't do it. Okay. So if you're curious, make sure you're punching your calculator right or wrong. Just, hey, Mr. Williams, flag me down. I'd love to help you out. Okay. So let's try this problem out. What is the kinetic energy of a jogger with a mass of 65 kilograms traveling at a speed of 2.5 meters per second? So let's draw a picture. We got a jogger. Let's see if I can do some. Okay, there we go. Do my best to do some jogging. There we go. We're going at a velocity of 2.5 meters per second with a mass of 65 kilograms. What is the kinetic energy? Well, let's try it out. Kinetic energy is 1/2 mv squared. So we got 1/2, mass is 65, velocity is 2.5 squared. So let's try it out. There we go. 0.5 times 65 times 2.5 squared. 203.125 joules. Cool. That's it. That's kinetic energy. Not too crazy. What I want to do now is, first off, did you guys notice the intro video at the beginning of this? Tons of fun. Spent way too much time making it. Anyways, energy's not really too hard. Kind of like you'll notice is that the math we needed at the beginning of the year is the same math we're going to use for the rest of the year. It's, can you identify the pieces you need? Can you put them in the correct spot? And then finally, do you know what your final unit is? Okay, let's try one more kinetic energy problem, and then we're going to connect everything together. We're going to connect potential and kinetic energy together. So this time we're looking for mass. I'm going to let you pause the video, try this out on your own, and see if you get the same answer I do. Okay. We got a baseball. Oh, that's not really good baseball. Let's try that again. There we go. We got a baseball. It's traveling at a velocity of 5 meters per second. It has a kinetic energy of 100 joules. What is the mass? Ooh, and this might be another situation where I made a baseball really heavy. I didn't practice this problem beforehand, so I might have made a baseball that really doesn't exist. Might be more like a medicine ball. Okay. Kinetic energy equals 1/2 mass velocity squared. Kinetic energy is 100. 1/2 mass is something we don't know. Velocity is 5 squared. Yeah, I made a medicine ball. There's no way a baseball would ever be this heavy. Okay, 100 equals 1/2. The first thing I'm going to do is square the 5. So 5 squared is 25. I'm running a little bit out of space. I'm going to bring this up here. So we got 100. Now what's 1/2 times 25? That's 12.5. One step away, and so we're going to say 100 equals 12.5. M divided both sides by 12.5. Oh, getting a little sloppy there. Mass is going to equal, is that going to be 8? Let's see if my mental math has treated me well. Sure is. 8 kilograms. Woo-hoo-hoo. Which is like 15, a little over 16 pounds. No baseball. It's gonna be ever that big. Maybe for a giant. Okay, that's it. We found the mass of a medicine ball, not a baseball. So let's put an exercise ball. Well, if I can spell correctly, there we go. Medicine ball, not a baseball. Okay. Let's now connect both potential and kinetic energy together. So at the very beginning we talked about how energy can't be created or destroyed, but how do they transfer in between? And if we look at a pendulum, you can actually see that really well. So a pendulum, you might have seen one in a grandfather clock. You might have seen one kind of in maybe your science class before. But a pendulum is usually a heavy mass that is connected by a string that swings back and forth. Well, what do we know? If we have this pendulum swing perfectly and like almost touch the ground, we can observe a couple of things. If the pendulum swings all the way up and stops for a brief moment, we can say the potential energy, let's try that again, that the potential energy is all, as 100% of it, is at the end. So the pendulum swings away, goes back, and it has 100% potential energy right here as well. Well, what's going on here? As the pendulum swings down, all of this potential energy is converted into kinetic energy at the bottom. So 100% of your energy is kinetic at the bottom. A couple things we can denote here. That the total energy stays the same. So total energy is conserved. We're also going to ignore air friction because technically over a long period of time this thing would slow down, but the energy is lost due to friction, which is in terms of heat, but we're going to just ignore air friction for right now. And we can say a couple things. That the pendulum will not ever go higher than its initial point. So however far back you pull a pendulum, it will not go any further. So this is your maximum height. Here and here. Okay. What can we then say about the pendulum at the bottom? And that would be your kinetic energy is the highest, which is the energy of motion. So then we could say at the bottom, it's going to have a maximum speed or maximum velocity. Okay, so let's see here for total energy is the same. That means we're going the highest height at the ends. Also means we're going fastest at the bottom, which means we can then say that the potential energy at the top of the swing equals the kinetic energy at the bottom. Because energy is not created or destroyed, it has to be conserved. So whatever energy at the top, let's say that is 10 joules, has to be 10 joules at the bottom. Again, we're ignoring air friction for now. And then it goes back to 10 joules at the top. So what we're going to do here for lab is that you're actually going to take a pendulum, you're going to bring it right to your nose, you're going to let go, you're going to watch the pendulum swing away, come back to your face and get really, really close. But as long as you didn't move, that pendulum shouldn't hit your nose. Shouldn't. If some people breathe, relax their shoulders a little bit and then get bonked on the nose. Okay, I believe there's one other thing we can unpack here. There's going to be one other piece, and that's going to be looking at mechanical energy. So mechanical energy, I'm going to call it ME. And I got to move that screen just a little bit. Mechanical energy of the system is going to be the potential energy plus the kinetic energy. Or we can also think of it as the total energy in the system. Since we're not looking at any other energy types, we can say the mechanical energy is the total energy, but mechanical energy is potential plus kinetic. Okay, you're going to be using this quite a bit when it comes to labs this week, looking at potential and kinetic energy, but we're going to kind of start to unpack it here. If you have any questions, let me know. Feel free to help you out as much as I can, and I'll hopefully see you in class soon. I forgot. I'm going to do these warm-up questions. You can do these warm-up questions with me, but it's kind of good extra practice to make sure you're still following along. Okay, what is the mass of baseball? It's a kinetic energy of 1,000 joules, traveling at 2.5 meters per second. Well, instead of 1,000 joules, let's do 10 joules. How about that? That, I believe, is going to be a little bit of a better number as far as true mass of a baseball. So since this is a kinetic energy question, kinetic energy equals 1/2 mv squared. We know the kinetic energy is 10, so 10 equals 1/2 mass times velocity squared. Okay, 2.5 squared what's that gonna be? 2.5 squared, isn't it like 5.25? I think that's really right. 2.5 squared, 6.25. Come on, Mr. Williams, you should know your math better than that. Clean this up just a little bit. So we got 1/2 times 0.625, and that gets me 3.125 m. Divide both sides by 3.125. We get the final mass of the baseball to be nope, I still didn't make a good enough of a baseball. I still made a baseball too heavy, so this is still another medicine ball. Should have tried the problem out earlier. Wah, wah, wah. Medicine ball. Okay. A 3 kilogram ball. Hopefully not a baseball again. Is at the top of a 10-meter hill. What is the potential energy of the ball? So we got a ball. It's at the top of a hill. Your height is 10 meters. Your mass is going to be 3 kilograms. And we're looking for potential energy. So potential energy equals mgh. Mass is 3. Gravity is still 9.8. And the height of your ball is 10 meters. So 3 times 9.8 times 10. Ooh, 3 times 9.8. 3 times 9.8. Not looking at my calculator yet. See, I haven't punched enter yet, so let's try mental math. It's 27 plus 24, so 27 plus 2.4, so 29.4. Nailed it. Times 10, so it's 294 joules. Got it. I can still do math. All right, last problem, and then we're going to kind of wrap up here and call it done. So, a 2 kilogram bird is flying, so we got mass, is 2 kilograms. Its height is 10 meters in the air. Its velocity is 2 meters per second. And we're looking for total mechanical energy. Well, earlier, what we just found out is that mechanical energy is kinetic plus potential. So if we find the kinetic energy or the potential energy, we can add those two together. So over here to the side, let's find the kinetic energy. So kinetic energy equals 1/2 mv squared. 1/2, your mass is 2, your velocity is 2 squared. So 4, 8, half of 4 is 4. Is that right? 4 times 2 is 8. Half of 4 is 4. Look at that. I still know my math. And potential energy. Let's do a different color for potential energy. Potential energy equals mgh. Mass is 2. Gravity is 9.8. And your height is 10. So 2 times 9.8 is 19.6. 19.6 times 10 is 196. Did I get that number right? 2 times 9.8 times 10. Nailed it. Potential energy is 196. Kinetic is 4. Let's plug it in and find the total mechanical energy of my bird. That's going to be 4 plus 196. So mechanical energy equals 200 joules. Sweet. And there it is, folks. We've officially done everything again. I'll see you on the next video or in the class. Take care.